Okay, so in part D, we have alluvial fans form where streams exit confined basins, as we saw in lecture. So these confined basins are areas of high energy, typically. So alluvial fans form when the areas of high energy enter an open area, a low energy environment, which allows the streams to spread out and distribute the sediment in that area of not being so confined, of low energy, okay? So a fan is made from one stream flowing from one point and depositing the sediment. Some well-known alluvial fans in Idaho occur near Mackay, such as the Elkhorn Creek alluvial fan, which is the figure above. So this is the Elkhorn alluvial fan, and this is in the Lost River Range. So it's pretty well defined, I think. You can see here a fan-like shape, right? These are all sediments, and so we're going to work with this picture. This would be the area that is relatively confined, right? Topography is kind of confining that. And so it has high energy. Suddenly you enter the valley, which makes it an open, low energy environment, which allows for this water to drop all the sediment as soon as it encounters the open, low energy area right here. So that's why you have so many sediments piled on upon one another. Okay, so question 23. Oh, and I'm going to take you through that in another document. All right, so again, question 23 says, what is the vertical height of the fan measured from point A to point B? So you see point A here, point B here. And so you have to determine what is the vertical difference. So subtract the lower elevation would be the elevation at A from the higher elevation would be the one at B. So it says, hint, count the topo lines and multiply by the contour interval. Okay, so that means that we need to figure out what the contour interval is, and we need to count the lines. So let's get this a little bit bigger so we know what's up. Okay, so let's start with this. So this contour interval right here is 6,800, and then if we count 1, 2, 3, 4, 5, it takes me 5 steps to get to 6,600. So that means that between 6,800 and 6,600, there are, hopefully you're thinking 200 feet. And if I take 5 increments to get to those 200 feet, each increment should be of, hopefully you're thinking 40 feet. So 200 divided by 5 is 40. So that means that each contour line is equivalent to 40 feet change in elevation. Okay? Good. So now we know that. That's going to help us as we figure out the vertical difference. Okay, so let's measure what elevation point B is at. So we know that B is pretty much lying at this contour interval. So let me draw. Okay, so it's this contour interval. I'm going to make this blue. Okay, so if I follow it along as closely as I can, that contour interval is thankfully about 6,800. Okay, so that would be my higher elevation. I want to subtract the low from the high. So 6,800 minus whatever A is at. So A is at this contour interval right here, right? But that doesn't fall on any index contour. So I need to figure out what that is based on a nearby contour. So I have 6,400 right here, and I know that each increment is of 40 feet. So if this is 6,400, the one below is 40 feet under that. The one below that one is 80 feet under this, and then this one is 120 feet under this. So if you subtract 120 from 6,400, that gives you, hopefully you're thinking 6,280 feet. So this is at 6,280. Sorry, I can't really draw numbers very well. Okay, so again, B was at 6,800, we had said. we calculated that A was at 6280, so that means that the operation should be 6800 minus 6280, which gives us, what is this, 5020 or 520 feet. So that's the change in elevation that there is between those two things. Okay, cool. So now you know how to calculate that change. And we had done this in the Topo Maps lab, but I just wanted to give you a refresher. Okay, so question 24 of your lab manual asks you, what is the elevation change upstream from point C to point D? So in this case, you're going to do the same thing we just did, but between point C and point D. So it's going to be tougher because there's a lot or many more topo lines within there. So let me go ahead and zoom in a little bit, show you how that's going to look. Okay, so you see that there's a lot more topo lines, so it's going to be a little bit harder to follow these contour lines. So I think in the answers that I give you on the Blackboard quiz, I give you options of, within 200 feet, but hopefully you'll get it within 100 feet or so. So if you follow this contour interval, you'll get somewhere around here. And the same thing for this one. This one's a little easier because the index contours are a little bit closer. Okay, cool. Okay, so question 25 says, for each of these portions of Elkhorn Creek, calculate the gradient. So I'm only going to help you with the first gradient from A to B. You'll have to do the other one on your own. So remember that gradient, the formula they give you right there next to the question? It's going to be, or the percent gradient is going to be the change in elevation over the distance. Those should be the same units. And then you're going to multiply that result by 100 to give you a percent. So that means that if we had our change in elevation to be 520 feet, we divide that by the distance, so that we have to calculate. And then that we multiply times 100, that should give us a specific gradient. So let's calculate that distance. So the way you calculate the distance is going to be through using these scales. And again, you want to use the scale of the same units. So because we use feet for the change in elevation, we want to use a feet scale here at the bottom for the change or the distance between the two. So here is a 0, as you can see, 0 feet or below, and then above, this is 5,000. So I have a little meter stick above it. That's about 5,000 feet. And I use that meter stick to put it in between B and almost all the way to A. So it's almost, or it's a little bit more than 5,000 feet. If you measure it correctly, it's close to 550, 5,500 feet in distance between the two. So if we do that, we know that that's going to give us about 20 or divided by 500 and 5,500. It's going to give us somewhere about 9.4%. Okay, so that will be the gradient. So again, if this is a gradient of about 30%, 9% is about this. So it's not very steep in your eyes. But once you start hiking that, it will become a lot steeper. Definitely not as steep as the gradient between C and D. So if you've ever hiked along the Lost River Range, you know that things are very steep. So for example, if you go to Bora Peak, you go up, I don't know, I think it's like 4,000 or 5,000 feet within 3.5 miles. So it's very, very steep. And that is what this upper part, the portion between C and D, represents. So again, the second part of question 25 is going to ask you the same thing, but to do it between C and D. So hopefully you'll use this scale here below to get the distance between them, and you'll get an idea of what the gradient is there as well, based on your previous answer to question 24. Okay, so this takes us back to the lab manual. Question 26 through 28 I'm going to let you figure out on your own. Some of these, if not all, are multiple choice questions or multiple answer questions in your exam or in your quiz through Blackboard. So you'll get an idea of what I'm looking for, but think about it before you go to the quiz. Think about what it could be that would enhance the sedimentation. For example, as they're asking you in question 28, how are the conditions going to help for that sedimentation or deposition to continue? Okay. So then question 29 is asking you, flip back to figure 3. What type of feature is highlighted in red, or rather circled in red? So I'm going to show you those two pictures or figures together so you know what they're referring to. So again, this is figure 3, which was on page 106. The figure or the area that they say is highlighted in red is the circled bit in red. So I made it bigger, and this is the same area as this part on figure 9. Okay, so it's exactly the same location, except that this is in 1938 and this is in 2018. Okay, so now you're going to be able to respond to the questions following the comparison of the two a little bit better. Okay, so again, comparing those two, what are the geological processes that would form the feature on figure 3? Again, the one that I circled in red. How has this area changed since 1938? What do you think is different now that you're seeing it here in 2018? And then what sorts of geological hazards should the residents that are living here be ready for? So that's also a multiple answer question on your quiz, but I want you to think about it before you go on to the quiz. Okay, so then after you complete part D, we move on to part E. So on part E, I'm not going to make you do all of it, but I'm going to make you do most of it. So part E, you need to refer to figure 10, which is the last figure on this lab on page 115. It's this picture, or figure, I should say. And you're going to have to work with that figure in order to determine these questions, in order to complete those questions. So it says, the entire area of land that is drained by one stream or river is called the drainage basin, as we saw in lecture. The topographic boundaries that separate basins from one another are called divides. So it is important to understand the boundaries or drainage basins to be able to predict anthropogenic activities, such as the effect of mining on a stream, which is this particular problem's idea. So your team has been charged with investigating some historic mining sites in Hell's Canyon, Idaho, that might be contributing highly acidic water into the Snake River. So the Snake River, as you know, goes through Hell's Canyon, and some of the creeks that are nearby it in this scenario might be contributing some of the acid from the mines above into the Snake River. So use a map on the following page, again figure 10, to determine which of these sites might need some environmental mitigation. So I'll help you with the first one. So in which stream would a raindrop that falls on location 1 eventually flow? So on what, not stream, but rather what creek within the, I guess it is a stream, what channel, what creek within the map would a raindrop that falls on location A flow? So if this is your figure, you locate location 1. So location 1 is right here. So luckily there are also, aside from the main creek, here or here, let me move me, or there's some other one down here. Aside from those, you also have like little channels that are feeding onto the creeks. So for example, you have one right here. So if a raindrop falls here on one, which of these creeks that I pointed out will it flow onto? So if we kind of follow, you see one, you see a little channel downstream. So again, how do you know what's uphill, what's downhill? You look at these contour intervals. So for example, this one is 4,600 and this one right here is only 4,000. So that means that this is lower. So the further, I guess that would be west that you go, the lower the elevation gets in this particular part of the map. So again, if you go from uphill to downhill, that's how water moves. You're gonna drop your water here, and it's gonna follow this channel. Gonna follow, 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 and then eventually it's going to come into Kirby Creek. So that'll be the first answer for question 32. And you do the same thing for all of these different locations. So for location 2, 3, 4, 5, 6. Okay.